Okay, this video is going to be how to solve some of the problems out of section 5.5. In this particular problem, we're to use the factor theorem to find all the real zeros for the given polynomial function and one of the factors. The factor theorem basically says if x plus 3 is a factor, then it must evenly divide that particular polynomial. That means that the remainder must be 0. If I can reduce the degree of the original down to something that's quadratic, I can then either factor it or I can use the quadratic formula to solve for the remaining zeros. So we're going to take this problem and its known factor of x plus 3, and we're going to reduce it to find all of the solutions to that polynomial equation. In this case, my original function is a cubic with a leading coefficient of 2, which means it has to be going down towards negative infinity as x goes to negative infinity, and up to positive infinity as x goes to positive infinity. I want to take either synthetic division or long division and divide with the factor x plus 3. If you do long division, you'll use x plus 3. If you use synthetic division, you will use the solution that goes with that factor, and the solution is negative 3. Let's set each one up so you can see what it looks like. In this case, what I'm going to have to start, if I do long division, would be x plus 3 on the outside, and then on the inside, hang on while I figure out what's up. And then on the inside, I would have the dividend, which would be 2x cubed plus x squared minus 13x plus 6. If I were to do long division, I should get the same result that I would get if I found the solution that matches the factor of x plus 3, and the solution would be x equal negative 3. So I could use the negative 3, and this would give me the same quotient and remainder. Remember that for synthetic, we only use the coefficients of the dividend. They have to be in descending order by the power on the variable, and I can't have any missing terms. They have to be filled in. Using synthetic division, I would get 2 straight through, negative 6 multiplying diagonally to the left, write it diagonally to the right, add down, I get a negative 5. Negative 5 times negative 3 is a positive 15. Adding down, I get a positive 2. 2 times negative 3 is negative 6, and we have our very first exact factor for the original polynomial. Because the remainder is 0, that means it factors it exactly. In other words, if I were to take the 2x cubed plus x squared minus 13x plus 6 and divide by the original factor x plus 3, I would get 2x squared minus 5x, I'm still having a little bit of trouble, plus 2. There is no remainder indicating that it exactly factored it. It also means by the remainder theorem that the ordered pair negative 3, 0 is on the graph. Since the y value is 0, this is an x-intercept. Let me correct the divisor so it looks a little bit more accurate. This should be x plus 3. Okay. Now, this gives me the first part, which is the quotient, but could I factor it more? And the answer is probably, possibly. Let's see if we can keep going. In other words, I have that 2x cubed plus x squared minus 13x plus 6 has to be equal to x plus 3 times 2x squared minus 5x plus 2. That's what the long division is telling us. Can I factor this second quadratic equation? Using the normal factoring process, I could try to factor it as 2x and x. If I did that, I would need the signs in the middle to be the same because the last is a plus, and they would both need to be a minus. I need them to add together to give me a -5. If I put the 2 here and the 1 here, that would give me a -1x from the middle and a -4x from the outside. Adding those together, I do get -5x. This means that I have now completely factored the original polynomial, and from here I can immediately tell that my x-intercepts are going to be at -3, 0, the original, 1/2 0 from solving 2x minus 1 equals 0, and 2, 0 from solving the last. By looking at the equation in its non-factored form, I can immediately see that the y-intercept when x is 0 is going to give me 6. This would be enough to draw a vague outline of what the graph looks like. Let's look at another example. In the next one, we're told to use the rational zero theorem to find all zeros. There are two names for this theorem. You're going to hear them both. So it's also called the rational root theorem, where a root means it could have come out of the quadratic formula. A root, a zero, an x-intercept, and a solution are often used interchangeably or like synonyms when we're talking about the real zeros of an equation. Let's take a look at what the rational root theorem or rational zero theorem says. The rational zero theorem assumes that you have your polynomial written in descending order, highest power, second highest, and so on, down to the constant last. It wants you to take the constant and put it in the numerator, then divide by the leading coefficient, in our case a 1. So this is going to be the constant or lowest degree coefficient divided by the leading coefficient. When you have this constant divided by the leading coefficient, there are all different kinds of ways to get those numbers. We're looking for all possible factors of 60 and all possible factors of 1. Now, 1 has only one factor, which is itself, but 60 has many. Let's list all the ones for 60. One of the easiest ways to do it is to make a list separated by commas and build your way to the middle. 1 times 60 is 60. The next number in line would be 2. 2 does divide 60. It's 2 times 30. What about 3? Yes. 3 times 20. As you work, you will see that the list begins to creep towards the middle. Hopefully you've left enough room and you won't run out of space. How about 4? Yes, 4 will go into 60. There are 4 15-minute periods in an hour, which is 60 minutes. So 4 times 15 is 60. 5. It ends in a 0, so 5 has to go. 5 times 12 gives me 60. What about 6? Definitely. 6 times 10, and yes, I am running out of space. What about the numbers between 6 and 10? The numbers in there are 7, 8, and 9. 7, 8, and 9 do not go into 60. Therefore, these are all the factors of 60. The factors of 1 from the denominator are just 1s. Since the factors of 1 are only 1s, then I put a 1 in the denominator. Now I can take any combination of any number from the numerator and any number from the denominator with either a positive or a negative. That is the rational root theorem. In other words, any of those might be a factor of the original. If I'm going to try to find them, I need to kind of locate where they are. There are other rules in your book that will help you find them, such as Descartes' rule of signs. I am not going to test you on Descartes' rule of signs, but you are welcome to use it if you want. For now, you will just have to try some and see if you can find them. Now, I will tell you that on a test, I will give you guidance as to which one I want you to use, because it could take you a long time to find the right one. This gives you a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 numbers with either a plus or a minus is 24 numbers to check using synthetic division. Now, this is not the most efficient way. Normally, I would produce a graph to see what it looks like. Let's take a look at a graph I produced on Desmos to help us graph this. On the left side of the screen, you can now see where I have pasted in a graph of what this function looks like. I'm going to blow it up a little bit so we can see if we can tell where it looks like it's crossing in order to know which ones to check. If we look at the x-axis, do you see that it looks like it's crossing here at 4 and maybe again at 5 and possibly at -3? Any of those makes a good choice to try in the rational root theorem to see if they are factors. I'm going to start with 4 or 5 since those are easier numbers to work with. In this case, note that 4 and 5 and -3 would all be in the list of possible rational roots. Let's start with 4. If I think 4 is an x-intercept coordinate, then the solution is 4, but the factor, of course, would be x minus 4. So to check that, I'm going to use synthetic division with 1, -6, -7, and 60 being the coefficients of the original polynomial in descending order. Now I draw the horizontal line. I get 1, multiply diagonally to the left to get 4, add down to get -2, multiply diagonally to get -8, add down to get -15. -15 times 4 is -60, add down. If I do not get a 0, I didn't find a factor. The factors only occur when the remainder is exactly 0. In this case, the remainder is 0, so I know that x minus 4 is one of the factors, which means that I can factor that original polynomial as x minus 4 times the quotient, which is x squared minus 2x minus 15. This is coming from the numbers in the quotient 1 degree less than the original. Now can I factor this? You can, in fact, continue going with synthetic division if you want to, or you could factor it directly. Since I thought 5 was also a solution, let's try and see if 5 will go into what's here. Notice I can hook the next synthetic division on directly since my previous remainder was 0. If I check 5, the 1 drops through, multiply diagonally to the left to get 5, write it to the right. Add down to get 3, multiply diagonally to get 15, add down to get 0. Did it work? It did work. That means that since the solution is 5, the other factor that corresponds to it is x minus 5. What is the remaining factor that's left? This is x plus 3, which is what I suspected from looking at the graph. Again, on an exam, it would take too long to check all 24 possible numbers. I will tell you which one to check, so you will know whether or not you're checking the right one. Let's use this to find all of the zeros. The zeros are the x-intercepts, also called solutions or roots. So roots, solutions, zeros, and x-intercepts all refer to the same thing on these graphs. My solutions are 4, 5, and oops, I've lost my plus. It should be plus so that I get -3 for the solution. Let's take a look at the next problem. Let's apply the rational zero theorem again to find all the real zeros. Take the constant at the back, or the last coefficient when written in descending order, and divide it by the leading coefficient. Do not reduce. If you reduce, you will lose some possible solutions. What are all the factors of 2? The factors of 2 are 1 times 2. There are no others. 4, however, has 2 pairs of factors, 1 times 4 and 2 times itself. So it has 3 integer factors of 1, 2, and 4 with either a plus or a minus sign. What are all the possible combinations I can make where I have a 1 or a 2 in the numerator, a 1, 2, or 4 in the denominator, with either a positive or a negative? I could have a plus or minus 1, plus or minus 2, plus or minus 1/2, or a plus or minus 1/4. This comes from 1 over 1 and 2 over 1, 1 over 2, and 1 over 4. What about 2 over 2? Well, that would reduce to plus or minus 1, which is already in my list. What about 2 over 4? That would reduce to plus or minus 1/2, which is also already in my list. This gives us 2, 4, 6, 8 different possibilities to check. This time, for fun, let's not look at the graph and let's just see if we can find one. We're going to start with 1/2. If we start with 1/2, then I'm going to write the coefficients of the original polynomial in descending order by the power on the variable. 4, -4, -7, -2. I'm looking for a precise remainder of 0 to prove that x minus 1/2 is a factor, giving a solution of x equal 1/2. To complete the synthetic, I would get 4. Half of 4 is 2. Adding down, I get -2. Half of -2 is -1. Adding down, I get -8. Half of -8 is -4. But when I add down, I get -6. It does mean that the ordered pair 1/2, -6 is on the graph, but it is not an x-intercept or solution. I'll try another number. Let's try -1/2. If I try -1/2, I need to start over with the original coefficients since I have not yet found a factor. This time I get 4. Half of 4 is 2. With the negative would be -2. Adding down, I get -6. Half of 6 is 3. A double negative makes it positive, so I get 3. Adding down, I get -4. Half of 4 is 2, and the double negative makes it +2. This time, I did get 0 for the remainder. That means that -1/2 is a solution, or x-intercept, and x plus 1/2 is a factor. Now I can take what's left and I can factor it directly, or I can continue with synthetic division. If it has an integer or rational number as a factor or solution, it has to be in this original list. If I were going to factor what was left, I would take off the 2 first, and that would leave me with 2x squared minus 3x minus 2. Does this factor further? I would get 2x and x, and if I need to subtract to get 3, I've got to have something bigger than 3. So I'll put the 2 to multiply by the 2 to give me 4 and the 1 there. Since they subtract to give me a negative, it should be minus there and plus there. That means that I actually end up having negative a half as a solution twice, which means on the graph, it will bounce at negative 1/2 before it crosses. If you had continued, you would also have found that x equal 2 is a solution. You could have taken the 4, negative 6, negative 4, and continued with synthetic. Just because we found negative 1/2 as a solution doesn't mean it can't be a solution again. And in fact, in this problem, it is. Let's do the synthetic to show that it is a factor again twice. 4 drops through. Half of 4 is 2, with the negative would be negative 2. Adding down, I get negative 8. Half of 8 is 4. The double negative would make it positive, so I get plus 4. There's my remainder of 0. This last one would be 4x minus 8 equals 0, which means 4x equals 8. And when I divide by 4, I get the remaining solution, x equal 2. Let's look at the next one. In the next problem, we're finding more than just real solutions. We're also finding imaginary or complex solutions with a non-zero imaginary part. However, the rational factor theorem is the same. Take the constant at the back and divide by the leading coefficient from the front. In this case, my leading coefficient is 1. 5 only has one pair of factors, 1 and 5. 1 only has one pair of factors, 1 and 1. This means the only possible rational roots I have are 1 over 1 or 5 over 1 or 5. One of those four numbers will have to be the rational solution if there is one. Let's start with 1. I usually start with the positives just to make it easier. So again, here we're looking for the leading coefficient and here for the constant. I'm going to start with 1. Put it into synthetic, pulling off the coefficients in descending order. 1, 3, 7, and 5. The 1 drops through, multiply diagonally to get 1, add down to get 4. Multiply diagonally to get 4, add down to get 11. These numbers look like they're getting worse. 11, add down, I get 16. That didn't work. Let's try negative 1. I have to start all over because I have not found a factor yet. You can only use the quotient part when your previous remainder was 0. This is going to give me 1, then a negative 1, 2, then a negative 2, 5, then a negative 5. There is my first factor. The solution is x equals negative 1, so the factor must be x plus 1. Now I have something that's quadratic. The quotient left over is x squared plus 2x plus 5 equals 0. I already have one solution over here of x equals negative 1, which is accompanying the factor x plus 1. Now I'm going to take this and see if it will factor. You can take a few minutes and try it, but I promise you it will not go. If it doesn't factor, then our only option is to either complete the square and solve using the square root property or to use the quadratic formula. I'm going to use the quadratic formula. In this case, I'm going to write down what the coefficients are first. A is 1, B is 2, and C is 5. The quadratic formula then gives me the opposite of B, for -2, plus or minus the square root of B squared minus 4 times A, which is 1, times C, which is 5, all divided by 2 times A, which is 1. To clean this up, I get a -2 plus or minus the square root of 4 minus 20, all divided by 2. 4 minus 20 gives me a -16. When I take the square root of a -16, the negative is going to create an imaginary number. The square root of 16 is 4. Now I'll split the quadratic formula into two separate fractions to be sure I reduce correctly. This will give me 4i divided by 2. This gives me -1 plus or minus 2i. How many solutions did we find? In this case, the original problem was a cubic x cubed, and I found 3 solutions: -1, -1 plus 2i, and -1 minus 2i. There are a couple things to notice about this. First, if the degree is 3, there are precisely 3 complex solutions. It could be that you find one of them more than one time, meaning it has a multiplicity of 2 or greater. Also, if you have a complex solution with a non-zero I part, they have to come in conjugate pairs because they're coming directly out of the quadratic formula. That means that they'll be exactly the same, except one will have a plus in the middle and one will have a minus in the middle. Complex solutions with non-zero imaginary parts always come in conjugate pairs. The degree of the polynomial also tells you exactly how many complex solutions there are. Complex includes real numbers with zero imaginary parts and complex numbers with non-zero imaginary parts. Let's take a look at the next one. On this problem, I need to use, again, the Rational Factor Theorem or the Rational Zero Theorem or the Rational Root Theorem to find all the possible numbers that I should be checking. While 24 sounds like a lot, it's nothing compared to infinitely many. The constant at the back is -30. The leading coefficient is 1. There are many factors of 30, 1 and 30, 2 and 15, 3, I'm running out of room, and 10, and 5 and 6. The only factors of 1 are 1 and 1. This gives me a list of a lot of different numbers: plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, and plus or minus 30. That's 16 different numbers. For this one, to aid us, let's start with the graph. If you look to the far left, you will see the graph produced for you. You can tell that the degree must be even because both arms go up. That also means the leading coefficient must be positive. Now when I'm looking at this, if I evaluate where it looks like it crosses, I would guess that it's crossing at -2 and at 3. Since both -2 and 3 are in my list, I'm going to just pick one and start. Usually positives are easier to use in synthetic division since you're less likely to mess up the negative. I'm going to start, therefore, with 3. If I can find the factor, then I can reduce it by 1 degree, so it'll go from x to the 4th to x to the 3rd. I still won't be able to use the quadratic formula, but then I can use the other factor of x equal negative 2 with the factor x plus 2 to try to break it down to quadratic. Let's write the coefficients of the original polynomial in descending order. 1, 3, negative 5, negative 29, and negative 30. Again, on the test, I will tell you which one I want you to try so that you will not have to check through a list of 16 different numbers or more. We're expecting this to work because from the graph, it does appear that it cuts exactly through the corner at 3, 0. Dropping through, I get a 1. Multiplying diagonally, I get 3. Adding down, I get 6. Multiply diagonally, I get 18. Add down, I get 13. Multiply diagonally, I get 39. Adding down, I get positive 10. Multiply diagonally, I get positive 30. Adding down, I get precisely 0. This is the remainder, which tells me that if the solution is x equals 3, then the factor has to be x minus 3 in parentheses. Now I'm going to try a different one. It's possible that 3 is a factor 3 times, but it cannot be a factor twice, because if you look at the picture, you can see that it definitely does not bounce at 3. If it's going to be a solution an even number of times, it would bounce, and it does not bounce. So now let's try negative 2. I can again draw the bar since my last remainder was 0, and I could try the negative 2 directly on the quotient of what was left. The 1 drops through again. Multiplying diagonally, I get negative 2. Adding down, I get 4. Multiplying diagonally, I get negative 8. Adding down, I get 5. Multiply diagonally, I get negative 10. Adding down, I get 0 remainder, which means it is again a factor and solution pair. So the solution is x equal negative 2 for the x-intercept negative 2, 0, and the factor it came from must be x plus 2. Since in the graph it does not bounce there either, then either it is showing up once or 3 times. Since the power is 4 and I already have 2 solutions, it's not possible for it to be there 3 times. I will have precisely 4 complex solutions to this problem. Now to find the remaining 2 solutions, I take what's left, the quotient, and I write it in its power or in its variable form, x squared plus 4x plus 5 equals 0. It is tempting to want to make the 5 end up giving you 4 by subtracting the 1x and the 5x. However, the last sign is plus, which tells you they must add. We need to use the quadratic formula because this will not factor. For the quadratic formula then, I'm going to go ahead and use the a, the b, and the c. A here is 1, b is 4, and c is 5. Then x will be the opposite of b, or negative 4, plus or minus the square root of b squared minus 4 times a, which is 1, times c, which is 5, all divided by 2 times a. This is similar to the last problem, though that's not the way it's always going to go. In this case, I get 16 minus 20, which will reduce to negative 4 under the radical. The square root of the negative 4 is going to give me a 2i coming out. To make sure that I correctly reduce it, I should go ahead and split it into two fractions and write -4/2 plus or minus 2i/2. And my thing is kind of wonking out on me again. This would reduce to -2 plus or minus I. How many solutions did we get? We got 4. We got 3, -2, -2 plus I. Oops, hang on a second. Move this up a little bit, see if it'll write a little better. -2 plus I and -2 minus I. Those are our 4 solutions. The last problem that we're going to look at is how do you construct a polynomial of least degree with the following information? They say least degree because you could find polynomials of greater degree that also meet those conditions. However, to find one of least degree, the answer should be unique. When it says the real roots are -2, -1, and -3, what they mean is when you solved, you got x equal -2, x equal -1, and x equal -3. Backing these up to their factor form, you would move the constant to the variable side to get the factors on the left and 0 on the right. That would lead to 3 different factors. The 3 factors we would end up with would be x plus 2, x plus 1, and x plus 3. To build my polynomial then, I have some constant at the front times the factors x plus 2, x plus 1, and x plus 3. If it had said the multiplicity was greater than 1, then the individual factor with higher multiplicity would have that multiplicity as a power. Now, how can I meet the condition that it contains the point 4, 2? This means that when I replace x with 4, the y value should be 2. So I'm going to replace the x coordinate with 4 and set it equal to the y value of 2. When I write this out, I'll be able to add these together to get a times 6 times 5 times 12. 6 times 5 gives me 30, and 30 times 12 gives me 360. Multiplied by a should be 2. That must mean that my a value should be 2 divided by 360, which is the same as 1 divided by 180. One function that will work here is 1 over 180 times x plus 2 times x plus 1 times x plus 3. If you wanted to get it into descending order, you would need to multiply out the factors 2 at a time in order to get the final answer. Let's do that on this one, just so you can see what the process is. First, I'm going to multiply together the x plus 1 and the x plus 2 factors. This would leave the 1 over 180 at the front and the x plus 3 factor at the back. In the middle then, I get x squared plus x plus 2x plus 2. That's using FOIL or the distributive property. This would lead to x squared plus 3x plus 2. I still have the 1 over 180 at the front and the x plus 3 factor at the back. Now let's multiply by the x plus 3 factor at the back. I'm going to leave the 1 over 180 out to the very end. The next step, I use a combination of both vertical and horizontal to help me keep straight what goes where. X squared times x gives me x cubed. X squared times 3 gives me a plus 3 x squared. X squared times, or that's the first two. Then distribute 3x times x gives me another plus 3x squared, which I'll line up under the first 3x squared. Then 3x times 3 would give me a plus 9x. I don't have any x's left at the moment, so I'll just put it out to the side where it would go in descending order. Then I distribute the 2 over the remaining factor. 2 times x would give me a plus 2x, which again is going to go underneath the other x term. 2 times 3 is 6, but I don't have a constant 6, so I move it off to the side where it would go. Now I can combine these into one polynomial, x cubed. 3x squared plus another 3x squared is 6x squared. 9x plus 2x is 11x plus 6. Now I can distribute the 1 over 180 to get 1 over 180 x cubed. 6 over 180 reduces to 1 over 30 x squared. 11 over 180 does not reduce, so I will leave it as 11 over 180 times x, plus 6 over 180 reduces to 1 over 30. This is what the function would look like in fully factored out and multiplied out form. What's the last problem on this homework set? This one says, construct a polynomial of least degree that meets the following information. Has a real root of 3, a complex root of 2i, and contains the point 2, negative 2. First, if I have a real solution of x equals 3, that means I have to have a factor of x minus 3. I have a complex root of x equals 2i, but complex roots with I parts have to come in pairs. There is no constant part or real part on this one, but I could think of this as 0 plus 2i, so I have to have its conjugate pair. The other conjugate would be the same, but with a 0 or negative on the inside, 0 minus 2i, or you could write it as, negative 2i. I need to convert the complex ones into factors. By subtracting the 2i and adding the negative 2i to both sides, I can convert the first factor into x minus 2i and the second factor into x plus 2i, just like I did with the real solutions. Now I want to multiply these together. This would give me, my F isn't looking too good, x minus 3 with some unknown a at the front times x minus 2i times x plus 2i. It's usually easier to multiply the conjugate pairs together first. This would leave the a and the x minus 3 hanging out front. This would give me x squared. The outside would give me a plus 2ix. The inside would give me a minus 2ix, and those would cancel. That's the conjugate pattern. Then the last would give me a negative 4i squared. If you remember, however, from earlier in the semester, I squared is equal to a negative 1. Since it's a negative 1, I can replace it with negative 1, and that will give me plus 4. So f of x so far is a times x minus 3 times the factor x squared plus 4, which does not reduce. The last piece of information I was given is that it does contain the point 2, negative 2. That means that the y value is negative 2 when I let x be 2. This will let me find the value of a. So I replace x with 2, and this will give me 2 squared plus 4, and this leads to a times negative 1 times 4 plus 4, which is 8, which gives me negative 8 times a. If negative 2 equals negative 8a, then this must mean that my a is equal to negative 2 divided by negative 8, or a positive 1 over 4. This lets me rewrite f of x as 1 over 4 times x minus 3 times x squared plus 4. This is the end of this video.